It looks like it's almost the academic 5 minutes has passed, or in Italy 15 minutes, so just gone 7, so we can kick off. First of all, an administrative matter. I'll circulate the attendance list, so do please sign in on that. I've been asked to mention that. I'm going to pass it round and pass it back. That's great. Then the other thing I have to do is to introduce our speaker for this evening, Mark Thomas from Microsoft Research, in all the way over in the west coast of the USA. Go to Seattle and then go out a little bit further and you get to Redmond, and there lives Microsoft. Many of us think of Microsoft as Word and Excel and PowerPoint and all the things that we love to hate about Microsoft. On the other hand, Microsoft is probably one of the most inventive and, dare I say, aggressive in research. I mean, aggressive in a good way. Progressive, maybe, is a better word. In audio, because customers of their software products expect to be able to interact with computers using voice and playback as well. The gaming side of software is a huge driver to what people want to do and are able to do with audio. And it's great to have Mark here today to tell us a little bit about array processing when it comes to Microsoft research activities, although I'm sure that he'll be prudent enough not to spill the beans on the latest version of the Xbox or whatever it is, which we don't know whether he's working on that or not. So Mark was a student and a researcher in this building for many years, so I've known him for a while, and it's a pleasure to be able to invite him back to give this talk all the way from the US via Italy, incidentally, to come and give us a talk here, closing the circle. And so I'll stop talking at that point and just introduce Mark Thomas. Thank you.
Well, thank you, Patrick, and thank you, the audience, for choosing to spend your Tuesday evening with me. I'll be looking mostly at the spatial behavior of microphones and how understanding of that spatial behavior can be used in the context of array signal processing. But before I go into that, I'd like to just give a little bit of background about myself. As Patrick said, I'm Mark Thomas. I am a researcher at the Audio and Acoustics Research Lab at Microsoft Research Redmond. And there I work on problems with microphone arrays. I do echo cancellation, noise suppression. On the rendering side, I've worked with head-related transfer functions, and we'll look a little bit about that later. And also on the rendering side with loudspeaker arrays. And we're always on the lookout for fresh, young talent in research. So if you have any further interest in what we do at Microsoft Research, then please do visit our website, research.microsoft.com. And I don't know what you've heard about the weather over in Seattle, but I assure you it's a little bit like London. It's mostly cloudy, but when it's sunny, like this picture I took a couple of weeks ago, it's gorgeous. So don't let that put you off. I guess you would say that I kicked off my engineering career working for the BBC in the research and development department at Kingswood Warren in Surrey. And there I was involved with some work with digital radios, some early work with high definition television and spectrum planning, and some hardware projects surrounding that. And then I moved on to Imperial College, where I did my master's and PhD thesis under the tutelage of my esteemed good friend Patrick Naylor. And then thinking I hadn't quite had enough of Imperial College, I decided to stick around a little bit longer and joined a collaborative European project called Scenic. And on this project, we were looking at the nature of reverberation. Traditionally, reverberation is seen as a bad thing for perceived quality and intelligibility of speech. And what we were trying to do is look at what useful information we could get out of reverberation. So, for instance, we wanted to work out where the dominant acoustic reflectors are, like the walls and the tables. So that's enough about me. First, to define what I mean by a directivity pattern. Well, directivity patterns are the response to a plane wave emerging from some known direction. So I say I've got a microphone, I've got some source somewhere in space that's producing a plane wave, and I want to know how it behaves as this source moves around it. Being that it's spatial, it has a function of azimuth. This is the angle on the horizontal plane. It's a function of elevation, or if you like, the colatitude angle, so it's a full 3D function. And it's also a function of frequency, or if you like, if we're working in the time domain, it's a function of time. This is what we call the far-field response. This is meaning that we are working with plane waves. Now, in the real world, we can't really produce plane waves. If you take a loudspeaker, it's going to be producing some spherical or near-spherical wavefronts. And so what we do is place those microphones and loudspeakers sufficiently far apart that we can at least assume an approximation of a plane wave. And practically, when we're placing microphones and loudspeakers apart, providing we go somewhere between 1 and 2 meters, we can say that this is a plane wave. The other point to note is that it's independent of reverberation. It doesn't matter whether you're using a microphone in an anechoic environment or in a cathedral. The directivity pattern doesn't change. It's something that characterizes the device itself. Now, like it or not, all transducers exhibit some kind of directivity. Sometimes it's by design and sometimes it's parasitic. So for instance, you might have a cardioid microphone that has some directional response. You would point the main response axis of that device towards the wanted talker, and then those talkers or other interfering sources that are spatially located elsewhere get suppressed. Sometimes it's parasitic. Inevitably, if you're going to make a consumer device, you have to place the microphone inside some kind of casing, and this may introduce some form of spectral distortion, or it may introduce some reflections, or worse still, some resonances, and this parasitic directivity is always going to happen. So what I've done here is taken from the DPA website 3 radial patterns from 3 of their microphones. So on the left we have what should be an omnidirectional pattern. So this means that we have no particular preference for sounds coming from any particular direction. It's equally sensitive everywhere. And what we see is that at 1 kilohertz we have a circle, we have an omnidirectional response. Then as we go up in frequency, it becomes increasingly directional. So we have this parasitic directivity. In the middle, we have a cardioid response. And we see that around 1 kilohertz, we have this heart-shaped cardioid response. This is a very classic shape in microphone design. But as we go down in frequency, we see that this dilates and it becomes increasingly omnidirectional. So we've had the opposite problem with the omnidirectional microphone. And the same thing happens when we have different types of directivity, like the shotgun microphone. So here we see an example of directivity both by design and as parasitic directivity. Another example of directional behavior is the head-related transfer function, or HRTF. And this characterizes the acoustic properties of the head, and that enables us to recreate 3D audio over headphones. What we see in the middle here is the measured head-related transfer function for my right ear, and this is at 1 kilohertz. And what we see is that the ear is much more sensitive on the right-hand side than on the left-hand side due to the acoustic shadowing of the head. It's also slightly more sensitive to the front than on the back because of the presence of the pinna. And what we see on the right-hand side is the same thing, but now taken over the horizontal plane only. With the y-axis we put on frequency. And what we notice is that around 10 kilohertz we have this notch. This is called the pinna resonance. It's caused by the resonant frequency of the inside of the pinna. And this is very characteristic of HRTFs. All HRTFs will have this. It might move up or down in frequency, or it might change its Q, but you'll always see it there. And you may have noticed if you look at the data sheets of some headphones, there is some approximation to this notch. And what that does is make sounds appear as if they're coming from slightly outside the head, and it's supposed to give a slightly more pleasant experience. We also see directional behavior in loudspeakers. So this is the dual case. We call this the radiation pattern. And we have here the measured radiation patterns for this model of loudspeaker. And we see, like with the microphone, at low frequencies, so around 200 hertz, we have a fairly omnidirectional response. And then as we go up in frequency to 1 kilohertz and then to 10 kilohertz, we come increasingly directional. So I hope I've shown that directivity patterns are interesting. They're an interesting thing to be looking at. And what I'd like to do is, in the remainder of the talk, split it up into two parts. The first, we'll look at the practical problems with the design of a measurement rig, how we take a device and measure its directivity pattern. And this includes the choice of test signal, where we choose to place our measurement loudspeakers, and then what we do when we have missing data, with having to do interpolation or extrapolation of missing data. Then in the second part, which is a little bit shorter, I'll look at practical applications, first in a beamforming scenario with a concrete example with the Microsoft Xbox Kinect for Xbox 360, and also in the case of head-related transfer functions. The first thing we need to do is design some kind of rig that will measure the directivity patterns. The first thing it needs to do is be able to reliably measure the linear impulse response, or if you like in the frequency domain, the transfer function between a loudspeaker somewhere in space and the microphone under test. The loudspeaker has to be spectrally flat. If it's not spectrally flat, then that introduces distortions, and then we don't know whether the signal that we're receiving is a function of the device under test or a function of the characteristic frequency response of the loudspeaker. So usually you have to perform some form of compensation to first flatten that frequency response. We must also be able to move sources to a precise and repeatable location. We need to be able to place the microphone in the rig and then be able to measure it twice in exactly the same way. We already said that the source has to be sufficiently far away to avoid near-field effects, and also the environment that we record in must be anechoic. Or if it's not anechoic, then the rig has to be sufficiently far away from acoustic reflectors so that we can suppress any effects caused by these local reflections by truncating the resulting frequency, truncating the impulse response. Now, the test signals are played in such a way that we can estimate the linear impulse response. So we can say that this is a finite impulse response problem. So we have some source signal that we will call U of n. This is what we play out of the loudspeaker. We then record back a signal that we call D of n, and this signal has been filtered by some unknown filter, which we'll call H. And what's nice about this kind of system identification problem is that it's what's called a convex problem. It's always guaranteed to have a unique solution, a unique minimum. And it's the job of the system identification to try to minimize the difference between this output D, we'll call this the desired signal, and the estimated filter signal Y, so as to estimate this signal H. So we have a filter H and we have some estimate H hat. Now, in the majority of cases, we can find closed-form solutions to the problem. We have an input, we have an output. We can solve systems of equations that will give us the answer within one go. Sometimes you want to do this adaptively, and this usually happens when we have a case with changing impulse responses. And the classic case for adaptive solutions is when you have a hands-free telephony problem. You have your loudspeaker in your mobile phone, and this is producing sound that is going to be picked up by the local microphone. Without an echo canceller, which is adaptively estimating this transfer function, the sound emitted by the loudspeaker is going to be returned to the far-end talker, and this can be very disconcerting. Now, there are some cases in the context of directivity pattern measurement that also call for adaptive solutions, and we'll look at this a little bit later. Now, the first problem that you come up against is how to choose your source signal. And I've split this up into three different types. The first type is what I call the chirp-like. So this is when we take a single frequency and sweep it as a function of time. And what's nice about this is that it's very intuitive. You can think of the magnitude response of your system as being the amplitude of the signal that you receive back. So you play back a sinusoid, you get back a sinusoid, and you can estimate the magnitude response by the level that comes back to you. So this is very easy to produce. It's just an oscillator. It's also very intuitive. But the magnitude response isn't enough. We also need to extract the phase response in order to get a full characterization of the system. Unfortunately, there's no real structure that can be exploited with the linear chirp. And so we have to use more generalized methods to estimate the impulse response or the transfer function. Another type of chirp-like signal is the time-stretched pulse. And this is a very carefully structured type of chirp that has a forward filter and an inverse filter. And they are both very compact in support, and what this allows us to do is estimate the impulse response of the system very, very quickly. And it gives us a very efficient means of finding the impulse response. It's also been shown to be very robust to non-linearities. So you have a loudspeaker and you're playing sounds with that loudspeaker. It's not a perfectly linear device, and sometimes this introduces some distortions, but the time stretch pulse approach has been shown to be fairly robust to these distortions. The problem is that you are concentrating energy in a very narrow spectral band as it sweeps up in frequency. And you can think of the loudspeaker as a cone that's moving backwards and forwards. The cone is made of material that's not infinitely stiff. It's got some degree of flex to it, and there are certain modes at which this will oscillate. And this produces nonlinear distortions. It's what we call cone breakup, and this is particularly prone to happen when we have single point sinusoids that are swept in time. Another type of signal is to use the pseudorandom noise. There's a class of signals called the maximum late sequence. There's also the perfect sequences. These have some very nice properties. They have autocorrelations that are perfect impulses, and they also have very nice structure that can be exploited to estimate impulse responses very quickly. Unfortunately, they have been shown to be sensitive to nonlinearity, so if you're driving loudspeakers quite hard, you can end up having some funny artifacts coming out in the estimated impulse response. Alternatively, you could use Gaussian noise, very easy to generate, and the autocorrelation of Gaussian noise is theoretically a perfect impulse, providing you have enough of it. And there are some low complexity but less accurate ways of exploiting this near autocorrelation, or you can use more generalized methods that are a bit more computationally complex. But what's nice about this kind of signal is that it's spectrally white. It means that we are spreading our energy over all frequencies as well as all times. So it means that we're not exciting any one frequency at one time. And this means it's less prone to causing cone breakup issues with the measurement loudspeaker. The third type of signal, which I guess is at the other end of the spectrum, is to excite the signal with a direct impulse. So imagine you have a test signal that in the digital domain has one non-zero sample. What's nice about this is that the signal that you record back is by very definition the impulse response of the system. And in the analog domain, people have used it in the context of room acoustics by creating gunshots and using clickers and little explosives. This is one way of measuring the impulse response. The problem is that we're concentrating all of our energy in a very short period of time. And it means that in order to achieve good signal-to-noise ratio, we have to have very high amplitudes. And the problem with doing this is that we have a tendency to produce nonlinear distortion in the loudspeaker. And for this reason, we tend not to use this direct impulse response approach when we're trying to estimate directivity patterns. So let's say that we have chosen our test signal. The next problem that we come up against is, where do we place our loudspeakers? Well, one approach is to perform an equiangular sampling. So you take an array of loudspeakers, in this case 16 loudspeakers that we have at Microsoft Research, put them on a semicircular arc, and then sweep this arc through space. And what's nice about this is that we can get practically continuous azimuth. We can steer it to any angle that we like. The colatitude angles are fixed due to the fact that we have fixed loudspeakers that we're moving around. So if we want to estimate the transfer function in between those loudspeakers, we have to have some form of interpolation scheme. And I'll be looking at interpolation a little bit later. Another problem in this case is that purely due to size constraints, we're missing data for a wedge underneath us. We can steer this arc, but only so far down. So we've got this wedge of missing data. And so this is what we call an extrapolation problem. We have to have some means of estimating the data that comes underneath us, and that's another problem that I'll look at later. Also, it's mechanically quite complicated. You've got 16 loudspeakers, you've got cables to get to them, you've got to be able to move it around to a precise location. It's quite heavy. You also have to be able to measure the position it's in. It's not the kind of thing that you can just go to a shop and buy. It's very custom hardware, so that takes a lot of effort to do. Another thing that may sometimes be a problem is that the sampling scheme that you come out is non-uniform. This will always happen when you have an equiangular sampling scheme. And so what we see in this figure here, we have a clustering of points around the poles, and sometimes this can be considered to be a problem. And there are variations on the theme. Sometimes you have a single loudspeaker, and sometimes you rotate the device under test. But it's a similar kind of idea. You've got one thing rotating relative to another. What you could also do is say, well, let's not have the complicated arrangement of moving loudspeakers. Let's instead just put loudspeakers in space, and we'll place them in such a way that they are uniformly distributed on the surface of this measurement sphere. There are some geometric solutions to this problem, and quite surprisingly, there are actually only 4 solutions for which you can achieve perfectly uniform sampling. In other words, the distance from one loudspeaker to the neighboring loudspeaker is constant. It's quite a surprising result, and it turns out that these positions are given by the vertices of certain uniform polyhedra. This is the first 4 cases here. So you can imagine the polyhedra with a bounding circumsphere. We could place a test loudspeaker at each vertex and then point that in towards the centroid of that sphere. But this only takes us up to 12 points. If we've got this equiangular scheme, we're able to measure sometimes 512 points or more. So 12 is not very many. There are other geometric solutions that get us close to near uniform. So we've got near uniform sampling, but not completely uniform sampling. And these have various strange and exotic names that I'm not so familiar with. But these are geometric solutions that take us now up to 24 points. But 24 is not so high. We want to get much, much higher than this. What's left are numerical solutions. Fortunately, we're not the first people to come across this problem. J.J. Thomson did a lot of work on electrons and the behavior of electrons. And he postulated this thought experiment whereby you take an electron and you bound it to be somewhere on the surface of a sphere. The potential energy of a single electron is constant no matter where you put it on that sphere. Imagine if you then add a second electron. They're going to repel one another until such a point that they are as far apart as possible. This then gives us 2 poles. That's the minimum potential energy configuration. We can then add a third electron, and this will then give us a triangle that lies somewhere on the great circle. So you can imagine an equator drawn somewhere. Then by the time that you add the fourth, then you end up with a tetrahedral arrangement. So this is the very first response that you get when you do the geometric approach. If you want to go to higher orders, then you can formulate this as a nonlinear least squares optimization problem, for which there are several solutions. I use a solution by a guy called Jörg Flieger. What's nice about this is that as well as giving you the points, it also gives you a measure as to how non-uniform those points are. And they can be very useful in approximating continuous integrals by summations. There are several other uses. For instance, in the case of spherical microphone arrays, you have a fixed number of microphones that you want to uniformly distribute on the surface of a sphere. And we see on the top right here a 64-channel microphone array that I built at Microsoft Research. It also comes up in the context of geodesic domes. Buckminster Fuller famously did a lot of work on the behavior of these points and some of the mathematical properties of them. And every time I see a geodesic dome, I just want to stick loudspeakers on the outside and do measurements with them. And you can generalize this to higher dimensions. So we're talking here about 3 dimensions. You can go to much higher dimensions. And this has been shown to be useful for quantization schemes for coding. And I believe I once read that this was deemed to be one of the most important mathematical challenges of the 20th century. And there are still lots of things about this that we don't understand. But fortunately, in the 3D case, the solutions that exist are sufficient for us. The final type of sampling scheme is what we call continuous sampling, and I think this is a particularly beautiful approach. It was first proposed by Gerald Denzner, who is a researcher at the University of Bochum in Germany. And what he suggested was to take just a single loudspeaker and, for measuring a head-related transfer function, rotate the head of the person that's under test. So we place earplugs within the ear canal, we put microphones on the outside of the ear, and then we rotate that head. And at the same time, we play Gaussian noise continuously. And using this adaptive framework, we're constantly trying to estimate the transfer function between the loudspeaker and the ear. And the assumption is that if we move sufficiently slowly, then the adaptive filter will always be close to converged. And this means that we have a continuous sampling. And I think this is a very beautiful approach. The only problem really is that we're constrained to measuring on the horizontal plane only, which for head-related transfer functions can be sometimes sufficient, but it's very difficult to then use this kind of approach if you want to do a full sphere of measurements. But I think it's nevertheless a very nice approach. The final problem is when we have missing data. So I mentioned that in the equiangular case, we have a missing the area of data that needs to be extrapolated, and we may want to interpolate between points. And so we have this missing spherical wedge. Now, interpolation problems come up an awful lot. If you're trying to do resampling of signals in the time domain, for instance, you have an interpolation problem. If you're trying to resample images in 2D, you can also have an interpolation problem set up. And for these kind of problems, you can usually use polynomial or spline interpolations. And this is very good for that kind of case where you have Cartesian coordinate systems. What we have here is data that lies on the surface of a sphere, and this behaves a little bit differently. You can think of the sphere as being a 2D problem. We have an azimuth and a colatitude angle, but it lies in a 3D manifold. And so it's got lots of periodicity. It's got lots of periodic properties that aren't really modeled by polynomial or spline interpolation. It also doesn't account for the curvature of this space. And when you try to apply this kind of numerical solution, you end up with a numerically unstable solution. What tends to happen is that the data that you're trying to extrapolate tends to blow up in the region that's missing. So this isn't a very good property. What we need is an interpolation or extrapolation scheme that is suited to data that lies on the surface of a sphere. But before I look at the solution, I just want to show you exactly what I mean by extrapolation and interpolation. So we see here this is my head-related transfer function, the directivity pattern at 1 kilohertz. Imagine it as viewed from my left ear. And what we see is that we're missing 90 degrees of data. We've just got a straight line that's drawn between the known data on one side and known data on the other side. Extrapolation is filling in this missing data, and there's some degree of smoothing has gone on at the same time, but it's filling in this missing data. Interpolation is finding the points between that data. So here we have 512 equiangular points. In this case, we have 2,048 uniformly distributed points, and this is actually one of the Flieger solutions to uniform distribution of points. We appeal to these little things called the spherical harmonics, and these have lots of nice properties for data that lies on the surface of a sphere. They are the angular solutions to the wave equation in spherical coordinates, and they form what's called an orthogonal basis for functions on the sphere. They've been used and very heavily developed for the solving of problems in quantum physics for the orbital angular momentum of electrons. They're also very useful for wave field analysis with spherical microphone arrays. And you can think of the spherical harmonics as being to spherical space as the sine and cosine functions are to 1D space. They're a basis for the spherical Fourier transform. And when you perform a spherical Fourier transform, you can think of the coefficients as being in the spatial frequency domain. Much like we have going from time domain to frequency domain, we can go from space to the spatial frequency domain. The main difference really is that they have discrete solutions. We can have sines and cosines at any frequency we like. In the spherical harmonics, they happen to lie on discrete solutions. And they have what we call a degree n and an order m. This isn't so important. But I just want to show you what the first few spherical harmonics look like. So what we're doing is we're going up in degree. To the right, we're increasing order, and left, we're going to negative order. These are actually they're complex functions. So to plot them, what I've done is taken the real part of the positive angle, the positive coefficients, and put them on the right-hand side, and taken the imaginary part and plotted those on the left-hand side. And besides being quite beautiful, they have lots of nice orthogonality properties. If we take any two and sum up each point and sum over all space, then we get 0. That means that they are, by definition, orthogonal. And you may recognize the first two lines. On the very bottom, we have a sphere. This is like an omnidirectional microphone directivity pattern. On the first line, we have the dipole, or what we call figure of 8 responses. And these form the first order directivity patterns. And what we can do is combine a spherical component and combine a figure of 8 component, as I've done on the left here, to, in this case, form a cardioid pattern. And depending on the ratios of the omnidirectional to the directional component, we can produce a cardioid, a subcardioid, a hypercardioid, or if we remove the directional component altogether, we end up with an omnidirectional pattern. If the sphere that we measured were complete, we would have 512 points distributed around us in this equiangular scheme. But we don't have 512 points, we have 400 points. If we had the full 512, we could perform what's called a 15th order model. In other words, we go to the very 16th row of that triangle, and that will allow us to make a very good fit of the data if we had all of it. But we only have 400 points, which means that we can't just throw a 15th order model at it. We looked at this problem in a paper that we published at the UPSIPA conference in 2012 in the context of HRTF modeling. And what we did was take a Brühl-Kjaer head and torso simulator, and this is a mannequin that simulates the average anthropometry of human beings. It's supposed to be in a very average head. And we created a baseline measurement by first measuring it the right way up, and then dangling it upside down, and then getting the data that's missing. So we then had a baseline, full, complete set of measurements. What you can then do on the left-hand side here is take those complete measurements, form a fit of the spherical harmonics, and then reproduce it. And you'll have to take my word for it that this is a very good fit. It's very close. If we then take this 15th order model and just apply it to the missing data, we see in the center this very, very big lobe. So this very center is to do with the area underneath us. So clearly something's gone very wrong in this area in the center. Now, when we're fitting, we are solving a least squares problem. We're trying to find the coefficients that minimize the error between the true data and the fitted data in a least squares sense. And when you have these kind of least squares problems that are ill-behaved, they're ill-conditioned, a normal approach is to apply what's called regularization. Regularization is a very carefully chosen bias that makes the data behave a little bit better. So what I've done here is solved the same set of equations but added this little bit of regularization, and we can see it now no longer blows up. But the problem with doing regularization is that we are adding this bias to data that we know is already good. So we're actually slightly spoiling the data that's already good. What also happens is that we get this funny periodic behavior in this missing area. And this periodic behavior isn't really there. It's just a quirk of the least squares fit. It's as close as the least squares fit can get given the regularization that we add. Instead, what we proposed was to say, well, we have enough data to perform a third order model. You can prove that there's enough data to do third order modeling. So we take the data that we know, we then extrapolate it using a third order model, take this extrapolated data, combine it with the data that we do know, and then form a full 15th order model over the complete data. And what we get is something that is very smoothly varying and follows the trends of the data in the known region. We're not able to get the very fine details, but this information just isn't available to us. What matters is that we've got a very well-behaved approach, and we don't have many unknown values. So when you're performing regularization, you don't really know how much regularization to add. Here, we don't have any parameters to tune, so this is one nice thing, a property of this approach. Perceptually, if you take a head-related transfer function and perform this, then take a source and then place it beneath you and then play that over headphones, it behaves in a very pleasant kind of way. It's very difficult to quantify this, but it doesn't behave in an unpleasant fashion. So that's covered part one. We know how to take our test signals, we know how to place our loudspeakers in space, and we know how to deal when we have missing data or data that we want to interpolate. Now we'll look at a practical application, and first of all, beamforming. Now, if you're not familiar with a beamformer, at its simplest, it's fairly straightforward. Imagine you have an array of microphones in space. And imagine then you have a wavefront that's incident on these microphones. In this case, the microphone at the top will receive the wavefront slightly earlier than the microphone at the bottom. So there's some time delay of arrival. The simplest kind of beamformer is the delay in sum beamformer. We estimate this delay just by geometry. And then these filters here all just delay the signals in such a way that for a particular angle they sum coherently. And what I've done on the right-hand side here is create a 4-element linear microphone array, use it in the end-fire configuration, and then design weights, steering weights, that steer towards 180 degrees. And what we see is that we've got this lobe of sensitivity along 180 degrees. Two other things happen. with the delay and sum beamformer, you see that as we go to low frequencies, this response becomes increasingly omnidirectional until at DC we have a completely omnidirectional response. This is something that will always happen with delay and sum. It's a function of the geometry of the array. What we also see is that on the far right-hand side is these aliasing components. Now, if you're sampling a 1D signal, if you're sampling a time domain signal, you have the luxury of being able to put in an anti-aliasing or Nyquist filter. This means that you completely circumvent any aliasing components. When you have microphone arrays in space, there's no such equivalent of the Nyquist filter, so you're always going to have some degree of spatial aliasing. That, again, is something that is related to the geometry of the array, and it's something that you just have to live with. And you would normally design the geometry to make sure that the aliasing components don't cause problems. Another thing you could do is pose the problem as an optimization problem. So rather than just delaying and summing, we can say, well, we know the capture vector. That means that we know the kind of delays that we expect to have, and if there's any directional behavior, we can also model that behavior. You formulate this as a least squares optimization problem and say, I want to have constant directivity irrespective of the frequency. And what we see now on the right-hand side is the solution for a superdirective beamformer, and we see that at low frequencies we continue to have this directional response. There are some practical limitations. As you go down in frequency, what happens is we introduce more and more white noise gain. This means that the self-noise of the sensor starts becoming significant. So we can't make this frequency independent all the way down to DC. There comes a point where the white noise gain becomes so high that you actually start introducing distortions in the resulting signal, and you actually end up making it sound worse, not better. So you have to put some constraints on the white noise gain, and for this reason we have a small broadening of the directivity pattern at low frequencies. High frequencies, we still have aliasing. There's nothing we can do about that, but we just have to swallow it. Now, a practical microphone array, something you can actually buy, is the Kinect for Xbox 360. There's a new Kinect that's just come out, and in both cases we have a 4-element linear microphone array consisting of cardioid capsules. The Xbox Kinect also contains an RGB camera for looking at the person in the living room. It also has a depth camera, which is used for skeletal tracking, and this picks out the positions of the limbs, and as you move around it can track your skeleton, and this is very good in gaming scenarios. But we're interested in microphones. We don't care about pictures. You'll notice that on the underside there is some venting. There's venting on the underside, but there isn't venting on the front. And ultimately, what this means is that the directivity pattern changes as we go up in frequency. So on the left-hand side is the measured frequency response and directivity pattern at 1 kilohertz. And we can see this nice cardioid-type shape. That's about as classic a cardioid response as you'll ever see if you're going to record it with real data. But what we see is that as we go up in frequency, the response starts pointing progressively down towards the floor. This is because of the fact that it's vented on the underside. And what happens is if you design a beamformer, assuming that the beam is pointing straight forwards, but it's actually pointing towards the floor, you end up getting a very good beam that points towards the floor, and that means it's no good. So what we need to do is try to make a design that uses these measured directivity patterns, and also to exploit the fact that they don't all point to the floor equally. Some point down more at some frequencies than others, so we have some diversity, and we can exploit that diversity. One way of measuring the performance of a beamformer is to look at its directivity index, and this is the log ratio of the wanted signal to the sum of all unwanted signals, so spatially unwanted signals. For a single cardioid microphone, the theoretical directivity index is 4.8 dB. If you have an omnidirectional microphone, then you have no directivity, so you get 0 dB. And what we see here is the directivity index plotted as a function of frequency. And we see in this blue line, at low frequency, say around 1 kilohertz, we see this 4.8 dB directivity pattern. This is exactly what we expect. And then as we go up in frequency, it drops a little bit because of the fact that it's starting to point down towards the ground. In the green line, we have the response of a beamformer trained on the assumption that the microphones are cardioids and they're always pointing forwards. And we see that at most frequencies we get a gain from this. We get noise gain. We actually benefit from having more microphones. But there comes a point that when we get beyond 6 kilohertz, they start pointing really far towards the ground, and actually the beamformer ends up doing worse than the single microphone. So clearly we need to be able to use measured directivity patterns, and this is what we get with the red line. Up to around 3 kilohertz, we get a similar kind of gain, a little bit better than what we'd have with the 3D cardioid model. But ultimately, we can continue this good behavior all the way up to the top of the band at 7.5 kilohertz. So what we've got is effectively for free an improvement in the performance. When I say for free, all we're doing is changing the weights used to describe the beamformer. There's no extra computational effort at runtime. We're just doing more computational effort when we're designing the beamformer. What we also did was make a speech recognition task. So we designed the beamformer based on the measured response of a single Kinect, and then took a database of 10 Kinects and recorded several hours in a living room scenario. This included people talking in the background, various clatterings. It was done in a reverberant environment. So it was representative of the kind of living room scenario where people would use Kinect. And what we did was then look at the word error rate, the sentence error rate, and the perceived objective quality. And what we see is that if we just take the single best microphone, then our word error rate is somewhere up towards 20%. So this is really, really bad. If we then run the same system using the 3D cardioid model, we then get a 10% word error rate. So this is the output of the beamformer using the cardioid design. If we then do the same thing with the 3D measured model, we're down at 5%. Now this is the word error rate independent of a language model. By the time that you add a language model over the top that takes into account the kind of dialogue that you're expected to say, then we can get word error rates down to practically 0. So here we can see that objectively with measured directivity patterns and working on real databases that we can get an improvement. And just to show you what the directivity pattern looks like at 1 kilohertz, on the left-hand side here is the response for the single cardioid model, and then on the right-hand side is the response using the measured case. And it's a little bit tighter here. Actually, the differences at 1 kilohertz were not so extreme. This was all summarized in the paper that we presented at the IWANC conference in 2012. But there's one little snag. We recorded it using a single device. So we made a measurement on a single device, and there's always a danger when you've got a single device to overfit to that. Imagine if there was a quirk in the manufacturing, there was a little bit of tolerance that wasn't quite met, then we run the danger of designing really well for one device but not all other devices. Now this design is one of those least squares problems, and in order to reduce sensitivity, we can add regularization, just like we did before with the spherical harmonics. And what we see on the x-axis is the different amount of regularization that we add. As we add more and more, the response of the beamformer becomes closer and closer to that of a delay and sum beamformer. Delay and sum is the most robust kind of beamformer, but also the least performing. And what we see is that by adding a little bit of regularization, in this case, 0.1, don't worry about the actual units, we can see that a little bit of regularization works for the measured case and gets us a slightly better result than if we had just no regularization at all. Ignore the green line, just the blue line, no, ignore the blue line, just look at the green line. We see the response using the 3D model, and we see that eventually by the time that we add a little bit more regularization, we do a little bit better. So what this is saying is that from the outset, the 3D measured model is a better model than the cardioid model. And the results of this regularization task were presented at the AppSeeper conference also in 2012. So that concludes what I wanted to say about beamforming. The final case is the head-related transfer function, or HRTF. And we mentioned that it characterizes the acoustic properties of the head. It allows us to recreate 3D audio over headphones. And for this, there are two sets of filters. There's one for the left-hand side and there's one for the right-hand side. Now, the thing about HRTFs is that they are highly personal. They're a function of what we call anthropometric features, things like the head height, the width, the position of the ears, the height of the ears, the size of the resonant cavity in the pinna. So everyone has a different kind of HRTF. And they provide different types of temporal and spectral cues that we use to localize sources in space. One of the most prominent is the interaural time difference. So imagine you have a source in space. The time of arrival at one ear is going to be different to the time of arrival at another ear. And then this allows us to estimate where the source is to within a circle of confusion. So what we call the cone of confusion. The interaural level difference is the difference in the amplitude of the signal that arrives at each ear. This gives us another cue. But if they want to localize sources to a greater degree, if we want to estimate height information, or if we want to resolve the front-back ambiguity, then very subtle spectral cues come about, and this is what's produced by the resonances of the pinna. Everyone has grown up expecting a certain kind of response. Everyone has learnt their own HRTF, which means that if you use somebody else's head, you're going to have a slightly different HRTF. And then what people find is that sounds can tend to sound like they're either too high, or sometimes they can't resolve the sounds on the front or the back. The other thing that you use in order to localize sources is head tracking. So if you're going to make a real-time system that employs head-related transfer functions, then you need to be able to track the head and pick the correct HRTF so that a source appears fixed in space. And depending on whether it's on the front or on the back, when you turn your head, it's going to move in a different direction. So that's one last cue that you use. So it's not something that's so relevant to directivity patterns, but it's certainly relevant to making a working real-time system. We said that we can measure HRTFs by putting somebody in an anechoic chamber, blocking off their ear canals, placing a microphone inside each ear, and then measuring. Now, this is all great, it's very accurate, but it's also very expensive. You need to have a lot of equipment in order to do it. Another thing you could do is scan the head in 3D and then perform finite element modeling. If you get Kinect, Kinect comes with a development kit called Kinect Fusion, and this allows you to perform a 3D model of the head. You can turn your head in front of it, and it will build up a 3D model. And then once this gets released for the next Kinect, we'll be able to get down to very, very fine, near sub-millimeter accuracy. The problem is that finite element modeling, there are many different flavors, are very, very slow. It means that you could even spend several days for one single machine, so it's not the kind of thing that's very suitable for a consumer device. Alternatively, you could try to estimate it from anthropometric data, and this is what I want to talk about now. It's, of course, less accurate than measuring it directly, but it means that we have no invasive measurements. Instead, you can just measure the head height, width, position of the ears, and various other anthropometrics, and try to estimate the HRTF directly. And the approach that we used in a paper that we presented just last week at the ICASP conference is to say, well, let's grab a database of people. We can measure their anthropometric features, things like the head height and the width. We can also measure their HRTFs. And when we take a new person, we can describe that person as a sparse linear combination of other people. So top left here is me. In the middle here is Jens Ahrens, one of my former colleagues, and on the right is Ivan Tashev, my boss. And then this new guy, Piotr Belinsky, the guy who wrote the paper, has been described as nothing to do with me. His anthropometric features are totally unrelated to me. He's got an alpha component of Jens and an alpha J component of Ivan. So we have this linear combination, and when I say it's sparse, what we mean is that lots of the coefficients have been forced to zero. That's the reason why there's none of me, but there is some positive value for other people. This is not discriminative anyway. This is just an example. What we then do is say, well, we know these proportions for the anthropometric features. Let's combine the HRTFs with the same proportions. So what we're doing is taking the magnitude response of the HRTFs and then summing them with the same proportions. This then gives us a personalized HRTF for the magnitude response. Now, as I said, we have a lot of information from the interaural time delay, so the magnitude response is not enough alone. We need to preserve the time delay and get these interaural time differences. We use a slightly different approach for this. What we do here is take the average interaural time delay, the ITD contour, and we see that it's roughly a figure of 8 shape. So imagine that we've got a source that lies on this plane in front of me. It's what we call the median plane. This produces the same delay to both ears, so there is no interaural time delay. As the source then moves around to the right, we produce a maximum time delay with one sign. Alternatively, if we move it to the far left, we have a maximum time delay but with opposite sign. And this gives us this roughly figure of 8 response. And what we did in another paper was then to take this shape and then use the anthropometric features to estimate a scaling factor. And this scaling factor then is all we need to take the ITD contour and add it as the phase response to the already synthesized magnitude response. Now we have a synthesized HRTF. Thing is, it's very, very difficult to evaluate the perceptual quality of HRTFs. We've got lots of new degrees of freedom. If you have a speech coder or a music coder, you might be evaluating the perceptual quality for a single channel or for 2 channels. Now we've got a whole spatial component. And unfortunately, when you start doing subjective tests, the ability of somebody to locate a source in space is not necessarily correlated with their perceived quality of the signal. So surprisingly, these two are completely, or at least partially, independent of one another. There's also the risk of the uncanny valley. What this means is that as we crank up the realism, so too does the expectation of the realism. So if you're listening to a mono signal or a stereo signal, you're resigned to the fact that it's a stereo signal. You put it on in headphones, you're resigned to the fact that it sounds like it's somewhere inside your head and not outside you. This you expect. As you get the realism higher and higher, you start expecting things to sound like the real world. And there comes a point when you're realistic but not completely realistic, and that actually gives you a slightly worse experience than you would get if you were to just listen to a stereo signal on its own. This is what we call the uncanny valley, and this comes up in lots of other areas. It comes up when you're creating robots. So say you have a robot that's used in a production line. It's got movement in the same kind of way as a human being would have, but you know it's not human, and you don't judge it by human qualities. Then you start creating humanoid-like robots, and then you get to the point where you've got something like Lieutenant Commander Data in Star Trek. Not quite human, but definitely approaching human, and some people find this a bit creepy. And you can see very similar effects in HRTS. You get kind of right, but not quite there. So it's very difficult to measure the perceptual quality, and this is an ongoing problem. But fortunately, as engineers, we have various measures that we can use, these objective measures. One approach is to use log spectral distance. This is a measure of the spectral distance between 2 signals. And what we did was take this database of people and take the very best classifier, so we find the very closest approach to that person, and the very worst classifier, the very worst match to that person, and then this gives us some bounds as to how well we should expect to do and how badly we should expect to do. And we see that this sparse representation lies somewhere close to that of the best classifier. Alternatively, if we take the head and torso simulator, measure those HRTFs, and then look at the log spectral distance of that, we find that that's actually quite close to the worst classifier. So surprisingly, this mannequin that's supposed to be an approximation to the average human is actually not a very good approximation at all, for reasons that I don't fully understand, but partially because I believe the head is quite small compared with that of an average human. I don't know why it's so small. So to conclude HRTF synthesis, I would be right in saying that this is by no means a solved problem. It's the first thing we need to do is be able to reliably and consistently remeasure HRTFs, and for that we need some kind of measurement rig. And the subjective testing alone is a big problem. How is the perceived quality linked to the localization accuracy? How does listener fatigue set in? What is the nature of this uncanny valley? We don't actually know where it is, but we know that it's most likely to be there. And of the objective measures that we have, things like PESC, Perceptual Evaluation of Speech Quality, LCQA, log spectral distance, mean square error, these things that we normally use, these are great for coding signals for purely a quality standpoint. It doesn't tell us anything about the spatial response. And so we need new objective measures. So I'd like to wrap up now with some conclusions. Directivity patterns are everywhere, like them or not. And there are many practical methods for measuring directivity patterns, for microphones or for loudspeakers, and also for head-related transfer functions. We have some degree of choice on the kind of source signal, depending on the scenario that we're working with, the loudspeaker configuration, and we have some tools that allow us to filling in missing data. And this has practical uses in beamformer design. This adds no extra effort at runtime because we're just changing weights. It can be used in personalization of HRTFs, and one other area that I didn't mention is the design of loudspeaker enclosures, where we think of radiation patterns as opposed to directivity patterns. I thank you very much for your time, and I welcome any questions.
Thank you for this talk, Mark. It's,
thank you, Patrick.
Very stimulating. If anybody has any questions, we'll use the microphone. It's not for amplification, but it's for the purpose of the recording of the lecture. So if there are any questions.
What are the sort of computational requirements for running the HRTFs that you're generating with this scheme?
At its simplest, it's purely a convolution. You have a point in space, you have a source signal, you perform a convolution of filtering, just do that twice, one for each ear, and then that gives you some position in space. That's a first approximation. If you want to go further than that, you need to add reverberation, and that you can be seen as being lots of little convolutions, or if you're going to add a reverberant tail, there's another part of reverberation that you can add on top of that. Another thing that you would need to add is, say, the directivity pattern of a source. If you've got a loudspeaker, as you walk around that loudspeaker, it can get louder in some directions and quieter in some directions. If you're at the back, it's less, and there are fewer high frequencies than on the front, and that adds to the computational cost. So it's very simplest. You can have a very low computational cost, but if you want to add all these other things that add the realism, then you go up to require lots. You can end up saturating a few cores at a thought. Thanks.
Have you done any work, or can you describe what's being done in relation to masking in the spatial domain? It's easy to, we always talk about the frequency masking, but it's obviously the spatial analog to this too, of the sensitivity and selectivity we have is then when you put multiple sounds together and we're finding not being able to separate.
Yes. So there's, compared with what we have with a speech coder, we know an awful lot about spectral and temporal masking. There's relatively little available. What we do know is that we're much better able to locate sources on the horizontal plane than we are to get height information. And so we know that if you place two sources closely together on the horizontal plane, you can differentiate them much better than you can at different angles. How this behaves as an average of a lot of people is very difficult to say. These results are so preliminary and so subjective that it's very difficult to ask somebody what's better. On a scale of 0 to 5, how good is this HRTF? Some people will say, well, I can locate this source really well, but it sounds crap. Or they can say, well, this sounds really pleasant to me. I'm used to hearing stereo somewhere inside my head, but I can't hear it anywhere else. And so we have this whole multi-dimensional problem that we don't really understand yet. And this is what makes it interesting to some extent. But the level of masking certainly has an awful lot of subjective and ultimately objective measures that can be derived from that. But we're not there yet.
I've got two questions. The first, you told us lots of ways of making measurements in terms of the source signal, but you didn't tell us which one you used.
We use, well, I use actually both. It's either the maximum late sequence approach or we have a linear chirp, depending on which system we're using on that particular day at that particular time. So I would say probably I've used maximum length sequences a bit more. For my master's thesis, I was looking at nonlinear distortions in loudspeakers, and this is where the nonlinear sensitivity of MLS came up. So I used that quite a lot in the context of loudspeakers, less so in the context of measuring HRTFs and directivity patterns.
And also, you've talked about the HRTF and how to personalize that. Have you looked at the problem of equalizing headphones?
Equalizing headphones, what's normally done is when you buy a head and torso simulator like Brüel & Kjær, that has ears with built-in microphones, and so they can be compensated using these built-in microphones. What's been found is that as you add a little bit of spectral distortion, slowly you become tolerant to it. If you have that spectral distortion that's introduced by the headphones, or if indeed you're listening to the wrong HRTF, you find that at first things sound very strange, especially if you've got a complex scene. Things sound like they're coming from all directions and you can't work anything out. But over time, it seems that you get used to this, that you become tolerant to these spectral distortions. And I think, at least an intuitive reason for this is because your ears are constantly changing. If you've been up in an aeroplane and your eustachian canals get blocked, or if you've got a cold, or you've been swimming, I believe, at least as far as I'm concerned, the behaviour of my ears change. And it seems that there's some degree of adaptation that takes place, and you get used to these new spectral distortions. And when your ears suddenly pop a couple of days after having been on the plane, suddenly everything sounds very loud and very strange. And there's some adaptation time that goes on there as well. And I think the same applies for headphones, if some spectral distortion is introduced by headphones.
It's a very simple question. What do you use the array on the Kinect for? Where are you kind of going with that?
Well, the problem that comes up when you're using when you're trying to do speech interfaces is that you've always got a very large distance between the talker and the microphone array. And the other problem that turns up in the Kinect scenario is that you've got loudspeakers that are playing very, very loud sounds. If you're playing a game as well, then you've got a big echo cancellation problem. You've got to try to cancel those echoes. And if you perform an echo cancellation, what happens is that the residual echo, there's always going to be some amount of echo that's left over, that residual echo tends not to be very spatially correlated. And this is nice because if you perform an echo cancellation, then perform a beamforming, the fact that these signals are not very spatially correlated means that the beamformer is also very good at getting rid of some of that residual echo. Following that, you then have a noise suppressor or some degree of spatial filtering that tries to estimate the statistics of both the residual echo and the background noise. That suppresses it a bit further, and then the output of the pipeline is what is finally fed to the speech recognizer, or if you're doing a telecommunication scenario, then to your Skype client. So without this array of microphones, you don't perform such good echo cancellation, and also as you have spatial diversity anyway, you're going to inevitably point a much tighter beam, even in those cases where you don't have any residual echo. Right, thank you.
Do you see applications for these HRTFs and beamformers outside Xbox?
I expect so. I don't actually work for Xbox. This is purely a research topic that may make its way into something like Xbox, or it may make its way into some other telecommunications device, or some aid of some sort. I don't actually know ultimately what kind of product this is going to end up in. All I know is that it's an interesting problem for me, and it's an interesting problem for the research community. And so long as it remains interesting, and so long as that happens, then we'll continue to do research on it and try to understand it a bit better.
I actually had a question, because Mark, you showed at the beginning techniques for measuring microphone directivity. And in a scenario where we wanted to make the best possible sound recording, for a music CD or something like that, we might spend a long time thinking about what type of microphone to use and where to position them and how many to use and so on and so forth, and getting a good balance and what have you. But if we know how to measure head-related transfer functions, shouldn't we just get microphones that have the directivity pattern of ears? And these are going to be the most realistic. Well, that's a big question mark at the end there.
It would be realistic if it were your ears, for you, but not for anyone else.
So if I had in-ear microphones and I went and sat in a concert and recorded my in-ear microphone signals, would that be the ultimate in recorded sound recording and rendering?
For the reason that you won't have any head tracking. Your head, when you play it back, will be fixed in the same location that you listen to it. If you want to turn your head, you can't. What you want is a decomposition of the wave field that is independent of head rotation. So this is where things like spherical microphone arrays come in. You've got a distribution of points on a sphere. As a plane wave becomes incident on that sphere, we know how it behaves, we know how it scatters around the sphere, and we can compensate for that scattering to describe the sound field as a continuum of plane waves incident on the center of a coordinate system. Once you've got that kind of description, it's then completely independent of the rendering engine. You can render it over an HRTF, you can mix it down to stereo, you can do surround sound. This is ambisonics. This is a kind of a generalization of ambisonics. If you have that kind of representation, then you can use the HRTF. You can also perform a spherical harmonic transform and get that into an ambisonics-like domain, combine those, and also put on all the rotations over the top to make you feel like you're there. Now, if you were to remove the head tracking and compare a rendering that involves using a spherical harmonic transform on a spherical microphone array and your own HRTF, compare that with something that you did with your in-ear microphones, I can't say which is going to be more realistic. I'd like to think that you wouldn't be able to tell the difference. Certainly something that I'd like to try. But I think it comes down to head tracking. Head tracking is a huge part of making an HRTF sound realistic. Without that, you've got very limited cues to see if something's in the front or the back. The majority of people complain that in the absence of head tracking, everything sounds like it's behind you. And I would just make a stab in the dark that there's an evolutionary advantage to this, that if you can't see it, it's behind you, take a look or run away.
Yeah. And just a sort of a quick follow-on to that, all of this work on head-related transfer functions finds its application, I think, in the use of headphones for sound rendering replay. So does that mean that Microsoft is going to be competing with Apple to buy Beats?
I have no idea.
Perfect answer. Any other questions?
What I do know is I have a lot of good friends in Beats. I'd love to be able to work with them if possible.
Okay. Yes, here we are.
Just a comment to further what you were saying. I do a lot of binaural recording in concerts.
Yeah.
And what you're both grappling with is the practicality to a certain extent, and of giving up the head tracking, perhaps in the playback, as I do, and maybe even in my case, giving up the actual all the pinna cues because of my very approximate binaural rig, but it works very well in that it's a sit-down concert situation, and the moving the head is a smaller price to lose compared to bringing in a 128 capsule spherical array into the concert with you.
True.
Etc. So there's a balancing act, and it does pretty well. And I haven't been bothered in a room now, or with a PA system, or in a natural concert. The behind you business is not
Perhaps
off-putting or even absent. It's not a big issue compared to, you can really sense spaciousness, degree of spaciousness, and involvement in the concert with a fairly modest binaural rig.
But I think this comes down to the problem of performing subjective testing is, do you want something that sounds nice, or do you want something that's totally realistic?
Yeah.
And they're not necessarily correlated.
Yeah.
When you put your binaural microphones and listen to a concert, do you not find that spoils the concert?
No.
If you're there in the actual concert, you're missing the live recording in order to make an offline recording.
Yes.
In which case, at least the sphere doesn't get in the way.
They're not blocking my ears.
Okay.
They're next to my ears.
Oh, I see. Okay.
And I probably do it for 10 or 15 minutes out of a concert, then put them away because it's a bit of a distraction. But it's kind of a record of what the sound in that event was.
I understand. Yeah.
And very interesting to pick up your point there about not really worrying about the lack of head tracking or maybe the front-rear ambiguity not disturbing you in concert. Clearly, this is a very important difference between recorded music and audio for gaming. Because I guess if you're playing shoot-up games, I don't know what they're called, but I gather there are some, where people are shooting you from behind, you really want to have that immersive experience of realistic sound with spatialization. Whereas in a concert, as you say, basically it's in front.
Well, yes, but as concert music, as concert experience evolves with multi-loudspeaker rendering systems in the venue, and people are putting the sound there at that moment and that sound there at that moment, you want to be able to record that. But in the traditional sense of there's a performing group. Sorry. In the traditional sense where there's a performing group at the front or around you and they're more or less stable, that's not the point.
Yeah, and I think that's certainly the point when re-rendering in stereo. If you set up something like an HRTF arrangement or a Blumlein pair or something like that, as far as wavefields are concerned, that kind of arrangement doesn't actually make any sense. But when you happen to put them over loudspeakers, they sound pleasant. They give you a width, a spaciousness, and that's enough. That if it's pleasant to listen to, then in several cases that's all that you really care about. It's not about reproducing wave fronts exactly. It's about getting it to sound nice. So, yeah, I don't think that there will be one set of subjective tests. I think, as Patrick says, there are those scenarios for gaming, and there are this kind of scenarios when you're going to be listening to music, and there are probably other scenarios that we haven't even thought of that may require some other kind of subjective test.
One of the types of music that avoid the uncanny valley effect would be something artificial like radio drama. Now, the BBC did a test. I don't know if there's anybody here who remembers it, Private Peaceful, and that was on WebSource, and there were 4 versions with different people's real measured HRTFs.
Okay.
One of them was a clear winner. The curious thing was that that person's head was quite unlike anybody who found it the best effect. And I don't know if you've met that. And so I did work in the 70s when we were measuring loudspeaker directivities, particularly women with heavy hair found it varied according to whether they put the hair behind their ears or in front, and therefore it must be a slightly learned approach.
It's interesting you should say this, because when we were performing these experiments, we were looking at the most average anthropometric person and looking at the HRTF that happened to fit best in a log spectral term. And I know this person, and I think I agree with you. I think he looks quite unlike the majority of people. So that's a very interesting result. And is this published anywhere? Is this somewhere I could read?
Yeah, I can't really speak for the BBC. I only ever worked for them by accident. But the
Same here.
The BBC blog site has details. It's under Private Peaceful, which was a radio drama a couple of years ago, done using digitally generated head transfer functions. But the interesting thing is we must compare notes, because the person involved who had the best effect in general had a very big head and really quite flat ears, quite the opposite of me, for instance. But I don't know whether there is. We could perhaps generate.
That's interesting. What you say about the big head, because at least as far as the measurements that we've made, I've got a slightly below average head. Most people have got a bigger head than me. And I find that if I'm listening to the wrong HRTF and I'm just trying to localize a single source that's on the plane, I find if it's in front of me, it's in front of me. If it's on the side, then great, it's on the side. But I find that as the source moves, it suddenly snaps. There's a missing region in between. And only when I use my own HRTF or somebody close to mine that I find that I can get this region in between. I can't say subjectively what happens when heads are smaller than mine, but I've certainly found this snapping behaviour. And it's interesting that you should say that the best one was the person with the largest head. That's actually contrary to what I have found.
But it's height as well, of course, with radio drama.
Well, yes. With height, that's where the subtle spectral cues come from. So in the case where you've got a source in front of you, it doesn't matter how big the head is, you're going to have the same 0 interaural time difference. The height then comes from the resonance of the pinner, and that's something entirely different, something much more subtle, and something less understood than the time delay. The time delay is really easy to measure, and same with level difference.
I am confused. When we talk about knowing the HRTF in order to reproduce properly, are we talking about rendering over headphones?
Absolutely, yes.
Well, people who are doing computer games, are they not listening through loudspeakers?
Well, that's an entirely different problem. The problem with loudspeakers is always the crosstalk. With headphones, left ear hears left, right ear hears right. There's little or no crosstalk at all. As soon as you have two loudspeakers, then you have a crosstalk issue. And people have been looking at this for quite some time. If you want to read more, I have a couple of papers that you can find on my website that we presented at the recent WASPA conference, where we took an array of loudspeakers. And this tries to just point one beam towards the left, to the right, and then another beam towards the left, and try to minimize the crosstalk between them. And it's been found subjectively, I couldn't remember where exactly it's written, but providing you have about a 20 dB separation between left and right, you can get full lateralization. If you have less than that, then sources don't sound like they're far out, they start getting closer towards your head. You can do crosstalk cancellation in stereo cases, something that I haven't been involved with, but lots of people have worked on this before. In some respects, it's easier when you've got a big, long bar of loudspeakers because you have more degrees of freedom to play with. You can get much tighter beams and deal with head tracking issues.
A lot of first-person shooter games, you need to wear a headset anyway to talk to your buddies. So I guess in those kind of games, then you can just fully exploit HRTFs.
Yes, that's true.
Good. Well, at that point, I think we should probably close and thank Mark once again for not only the interesting talk, but all of this interesting discussion which followed on. So thanks very much.
Thank you very much indeed, guys. Thanks.